The first movement appears near a seam in the pavement. Not a continuous line, not yet. Just a few ants emerging from a narrow crack between concrete slabs, moving in short, irregular paths. Some pause, reverse direction, or circle briefly before continuing. There is no visible structure at this stage, only scattered motion along the edge where two surfaces meet. Over time, the pattern stabilizes. A loose alignment begins to form parallel to the seam. Ants approaching from different directions start to converge into a narrower corridor. The path is not straight in a geometric sense, but it becomes consistent in position. It follows the sidewalk edge, rarely crossing open pavement unless interrupted. This alignment is not accidental. It reflects a set of constraints imposed by the surface itself. Sidewalks present a broad, exposed plane. The center areas are relatively uniform, offering little variation in texture or cover. Movement across these open sections increases exposure both to temperature fluctuations and to disturbances like foot traffic. The edges, by contrast, provide slight depressions, micro shadows, and irregularities where debris accumulates. These features create a more stable corridor for movement. Ants do not evaluate the entire surface before choosing a path. Instead, their movement reflects immediate conditions. When an ant encounters a boundary such as the raised edge of a slab or a narrow crack, it tends to follow it rather than cross it. This reduces the number of directional decisions required. Instead of navigating a continuous plane, the ant moves along a constraint that limits its options. As more ants follow similar boundaries, their paths begin to overlap. This overlap produces reinforcement. Each ant deposits chemical traces as it moves, but the placement of these traces is not uniform across the environment. Along edges, where movement is already more likely, these traces accumulate more densely. The result is not a design trail, but a gradually intensified corridor where prior movement increases the likelihood of future movement. The sidewalk edge becomes a stable path not because it is optimal in all conditions, but because it is consistently usable. Alternative routes exist. Ants can cross the open surface, and some do. These crossings are typically shorter and more variable. They often appear when the destination lies directly across the pavement, but they are less persistent. Without structural guidance, these paths disperse quickly. Small deviations lead to divergence, and without repeated overlap, reinforcement does not occur. Edges, by contrast, reduce variability. When an ant follows a linear boundary, its movement is constrained to one dimension. This increases the probability that other ants will traverse the same line, even if they begin from slightly different positions. Over time, this produces a higher density of movement along these edges. Compared to the open surface, the trail is not a fixed structure. It adjusts continuously. If a section of the sidewalk becomes obstructed by water, debris, or repeated disturbance, the trail may shift. Ants encountering the disruption begin to explore adjacent areas. Some will deviate slightly from the established path, testing alternative routes. If enough ants pass through a new corridor, reinforcement shifts accordingly. This process does not require coordination across the group. Each ant responds to local conditions, but the aggregate effect produces a coherent adjustment. The sidewalk itself contributes to the stability of these adjustments. Concrete surfaces expand and contract with temperature changes, creating small cracks and seams. These features persist over time, providing consistent reference points. Unlike natural soil, which can shift more dramatically, sidewalks maintain their structure across longer periods. This allows trails to remain viable across multiple foraging cycles. However, stability is not absolute. Human activity introduces irregular disturbances. Footsteps, cleaning, and environmental changes can erase or weaken established paths. In response, ants do not attempt to restore a specific trail. Instead, they re-establish movement patterns based on current conditions. Often, this results in a path that resembles the previous one, not because it is remembered, but because the same constraints still apply. The edges remain favorable. Temperature plays a role in this preference. Open concrete can absorb and radiate heat, creating localized hotspots. Edges and cracks, even if only slightly recessed, can moderate these extremes. Movement along these areas reduces exposure to temperature spikes, especially during peak daylight hours. This does not eliminate risk, but it narrows the range of variability. The timing of movement reflects similar constraints, and activity along sidewalks often increases during periods when surface temperatures are lower: early morning, late afternoon, or shaded intervals. During these times, the viability of both edge and open surface paths improves, but the relative advantage of edges remains. Edges also accumulate organic material. Dust, small particles, and plant debris tend to settle along boundaries. These materials can provide both navigational cues and occasional food sources. While the primary function of the trail is movement between nest and resource, the presence of incidental materials along the path reinforces its continued use. The trail becomes a corridor where multiple functions overlap. This overlap is not planned. It emerges from repeated use under consistent constraints. Ants moving along sidewalks are not optimizing for a single variable. Their behavior reflects a balance between movement efficiency, exposure, risk, and environmental stability. Edges offer a compromise across these factors. They are not always the shortest route, but they are often the most reliable. Reliability, in this context, increases the probability that a path will persist. Persistence does not require permanence. It requires sufficient continuity that movement can be maintained across time. Even when a trail fades temporarily, the underlying structure of the environment supports its reformation. This is why similar patterns reappear in the same locations. A crack between slabs, a slight depression along a curb, a line of accumulated debris. These features remain after individual ants have moved on. When new ants emerge, they encounter the same constraints and produce similar movement patterns. The trail is not a fixed entity. It is a recurring outcome. As the day progresses, the density of movement along the sidewalk edge may increase or decrease, depending on resource availability and environmental conditions. The path may become more defined during periods of high activity, then fragment as movement declines. But even in fragmentation, the structure is preserved. Individual ants continue to favor the same boundaries. Small clusters of movement persist along the edges, ready to coalesce again when conditions align. By the time the surface cools again, the seam in the pavement hosts another sequence of aligned movement, not identical to the previous one, but following the same constraints. The pattern does not depend on continuity between cycles. It depends on the consistent interaction between the ants and the environment they traverse. The sidewalk does not guide them intentionally. It limits their options, and within those limits, a trail forms not as a design path, but as a stable response to a surface that narrows the range of viable movement. At the edge of the concrete, where the seam remains unchanged, the next sequence begins in the same way. A few ants emerge, pause, and align themselves along the boundary. The structure rebuilds from scattered motion into a narrow corridor, not because it is imposed, but because under these conditions, it continues to work.